Good afternoon, everyone. It's nice to be here, and I would like to thank the organizers for giving us an opportunity to talk about some of the work we've been doing in our group at Columbia. I hope you'll forgive me today because on a nice Friday afternoon, I'm going to talk to you about disasters. And I'm sincerely hoping my talk is not going to be one. But more precisely, it's about avoiding disasters. And the subject is how do we manage systemic risk in complex systems. So what is systemic risk? It is the risk that a large system may collapse completely, a total catastrophic failure, what people call as a systemic failure. Unfortunately, we have seen a number of these things happen in recent years. In the financial area, we saw the subprime crisis, which started in the US and spread globally, which led to the demise of several major financial institutions, such as the Lehman Brothers. In the area of earth and energy and environment, what you see there is the BP oil platform burning after an explosion in April 2010. This is the Deepwater Horizon oil spill as a result of an explosion which killed 10 people, spilled millions of gallons of oil into the Gulf. And to date, BP is facing about $40 billion in losses. In a different sector, in the power sector, what you see are the two pictures of before and after the Northeast power blackout, which happened roughly 10 years ago. The left is where the night before you see the northeastern coast lit up well, and then the one on the right is after the power failure, which affected 50 million consumers in the northeastern US and Canada, $6 billion in losses. In the public health domain, we have had a number of epidemics. What you see there is the SARS epidemic network. And in aerospace, we've had the Challenger and Columbia space shuttle accidents. And in 2010, Johnson & Johnson had to recall 130 million bottles of children's medicine, such as Tylenol and so on, due to a systemic failure in their supply chain, which led to major quality issues. And finally, perhaps the mother of all systemic failures is the one we are in the middle of. All the other incidents have happened already, whereas this one is unfolding right before our eyes. And experts tell us that we still have some time to do something about it, perhaps avert this crisis, or at the very least mitigate its effects. So these are all essentially disasters in different domains, some in the finance, some in energy and environment, power, and so on and so forth. At Columbia, at the Center for the Management of Systemic Risk, we study all these disasters and a dozen others, which I haven't mentioned, with the hope of understanding how and why complex systems fail catastrophically, how can we design them better so that these things don't happen, or at least monitor them a little more closely so that we can recognize the signs early on so that we can better control them and better manage the systemic risk. Now, typically when these things happen, immediately there are congressional panels or such inquiries set up. What you see there is the panel report after the Northeast blackout, where people get into the details of what went wrong and then provide a summary of recommendations about how to avoid these things in the future. Typically, these reports are several hundred pages long, but they focus on that particular event. And this is focused on the power sector. This is the BP Texas City accident in 2005 and in Houston. And this is the Madoff financial, the Ponzi scheme report. And more recently, these panels, two different panels produced reports on the subprime crisis as well as the Deepwater Horizon oil spill. Now, as chemical engineers, typically, we would read, for example, the Texas City report and Deepwater Horizon report in order to understand what went wrong so that we can avoid these things in the future, but we are not likely to read the reports from the other domains and understand what went wrong in the other cases. Now, from the way things are going in Wall Street, it looks like the finance guys are not going to read their own report, okay, let alone read reports from other domains. But there is value in comparing these accidents across these domains. Even though they seem very different, they all happened in different facilities triggered by different events. The materials are different. In one case, it's oil, the other case, financial instruments, and so on and so forth. But if you go beyond analyzing them as unrelated one-off accidents, but actually see them from a common systems engineering perspective, you begin to see some commonalities. There are some differences, of course, but you see some common underlying patterns, which are signatures of fragilities in complex systems, which I'll get to in a minute. So in order to do this, since they are all, it's a bit like comparing apples and oranges, you really need a formal, consistent framework where we can all put these things together and then compare them more or less equitably. And for that, you need progress at the intersection of two disciplines, which at the moment are not really talking to one another. One is systems engineering, which deals with the challenge of how to design, control, and optimize complex engineered systems, such as chemical plants, power grids, and space shuttles, and so on. And the other is the science of complex adaptive systems, which are found more in nature, such as in biological systems, ecological systems, and so on. So, looking at this from the systems engineering perspective, at the center, we are developing a systems theoretic framework, as shown here, a 7-layered model where we can go all the way from a plant level, from the equipment level, all the way to the top, through the intermediate levels of the hierarchy, where we capture decisions that are made at the management level or the regulatory layers, and so on and so forth. And this is the common unifying framework which can help us compare these apples and oranges a little better. And so we've been using this to tease out these mechanisms of failure that happened in the case of BP or in subprime or in SARS and so on and so forth. So what we see are the signatures that are common, as well as the differences. Both the commonalities and differences teach us valuable insights about how to model these systems a little better, how to monitor them a little better, and manage systemic risk a little better. So that's one line of attack we are pursuing. And the other one is from the perspective of complex adaptive systems. These systems are typically hierarchically organized, very large network of components and subcomponents which are interdependent, and then typically there are thousands of them, if not more, and they have complex configurations. You find them in the power grids, you find them in the financial networks in the US or globally. You find them in large-scale refineries, such as the offshore oil platform, and so on. And what makes it even more tricky is the nature of the interactions, which are highly nonlinear, and as a result of which, they exhibit emergent behavior. That is where the behavior of the whole system is much more than the sum of its parts. And all these things lead to potential fragilities, points of weaknesses, which can lead to potentially to systemic failures. Now, in the past, we have addressed complexity largely from the reductionist perspective. This is a top-down paradigm where we would take a large system and then break it down into its parts and then try to understand those parts, and hopefully that will tell us about what's going on. This reductionist paradigm was essentially the dominant scientific approach in the 20th century, and this was spectacularly successful. We were able to explain how macroscopic matter is made of molecules, which are made of atoms, which are made of nuclei, which contain protons and neutrons, which in turn are made of quarks, and now we are told they may have their own components called strings. And so this gave birth to quantum mechanics and elementary particle physics, and literally scores of Nobel Prizes have been awarded for making progress along this particular research direction in 20th century. And this program was so successful that we even applied it successfully in life sciences and showed how biology can be explained in terms of its molecular basis, with the crowning achievement of the discovery of the double helix structure and so on. So successful this program has been that my physicist friends are fond of calling string theory as the theory of everything, implying that it can explain everything that is going on in the universe. Now, I have a small problem with this claim in the sense that can it explain or predict emergence of life or the emergence of consciousness? We know that an individual neuron, loosely speaking, is not self-aware, but when you put 100 billion of them in a particular way, the whole thing is suddenly self-aware. It can ask questions like, who am I, why am I here, and how long is this boring lecture? Now, so the challenge that we face here is how do you go from the parts to the system, okay? And this is a completely different challenge. This is a completely different perspective. The reductionist paradigm is not going to help us here because this is bottom-up, whereas the reductionist techniques used analysis as the primary tool of investigation. This is more about synthesis. This is about putting things together. Now, at the dawn of 20th century, Lord Kelvin, one of the giant figures in thermodynamics, gave an interesting lecture at the Royal Society in London. The title was The 19th Century Clouds, or the Dynamic Theory of Heat and Light, where he mentioned that physics knowledge is almost complete, except for two small clouds that remain over the horizon. It turned out those two small clouds were a big deal because they completely revolutionized 20th century physics. In fact, they completely revolutionized 20th century science. One was the problems we had with black body radiation, which led to the birth of the quantum hypothesis through the works of Max Planck, and then subsequently to the creation of quantum mechanics itself. And the other is the null result from the Michelson-Morley experiment, which gave birth to special relativity first, and then the general theory later on through the works of Albert Einstein. I believe at the dawn of the 21st century, there is a large cloud hanging around the horizon. And this is this problem. How do you go from parts to the whole? And like I said, this reductionism can help us here and there, but it's not going to help us solve this problem because it's a different problem altogether. And this is basically addressing complexity from an integrative perspective. In the 20th century, we looked at complexity. We managed complexity through this reductionist paradigm. Now all the problems, including global warming, all these things we are facing require progress in the integrative perspective. And in particular, making progress in understanding how design, control, and optimization are done through self-organization, and how those things perhaps can give us some insights about how to develop a theory of emergent behavior of such nonlinear systems. These would require conceptual breakthroughs, not only in biology, but also in cognitive science, particularly artificial intelligence, and systems engineering. The systems engineering part is the one that has not been as well recognized and understood. So in all the discourses on this particular topic, you don't find systems engineering being mentioned that much. But I believe it is vital to the discussion here because it is an engineering where we put parts together and create a system. So of all the various tools we have at our disposal, from mathematics and physics, chemistry and biology and so on, they provide us largely analytical tools. Where we get the ideas about synthesis is only in engineering, because engineers are the only ones who typically create a system by putting things together. So I believe systems engineering is going to be a major component of this particular theory of emergent behavior. This will impact biology clearly, as well as various engineering sciences and social sciences as well, such as economics and sociology. And I believe this will be the dominant scientific paradigm of the 21st century. Just as the 20th century science was dominated by the reductionist philosophy, the integrative approach with systems engineering as a key component will be a dominant research philosophy as we look at challenges such as global warming, or how complex systems fail catastrophically, and how to manage systemic risk in the future. So let me stop at this point. I want to thank a bunch of sources where I've drawn the images from, and for your kind attention. Thank you.